Hello dear students. So in the last class we had discussed the uniform plane waves. We had derived the general wave equation for uh, the electric field intensity, electric flux density, magnetic field in flux density and magnetic field intensity. Okay. So we had discussed the short introduction of the waves also, that the waves consist of the electromagnetic waves consist of the components of electric and magnetic field. Okay, now from today we will discuss the uniform plane waves in free space. So let's continue the topic. So uniform plane waves in free space, in free space, this we have to discuss today. Okay, so let us consider, let us consider an electromagnetic wave. EM waves means electromagnetic wave propagating through the free space. Okay, so what is free space? Most of the time we consider air as a free space. Okay, so there free space means conductivity is zero, sigma is zero. Okay, because free space or air cannot conduct. Okay, so the conductivity in free space is considered zero. So this is sigma is conductivity. So now let us consider that that electric field is in x direction. The electric field is oriented in x direction. Okay, only, while the magnetic field is oriented in y direction, is along y direction. While the magnetic field is along y direction. Okay, now what is the meaning of plane waves? Plane waves means electric field vector E and magnetic field vector H lie in the same plane. Okay, so what is the meaning of plane waves? So the plane waves means what? Means that electric field vector E and magnetic field vector H. Okay, so electric field vector E and magnetic field vector H lie in the same plane. This is the meaning of plane waves. Okay, they are in the same plane. I am not talking of they are in the same direction. I am talking that they are in the same plane. दोनों सेम प्लेन में लाई करते हैं. Okay, means what I mean to say, let me draw with an diagram. So let us suppose that this is your z axis. Okay, this one is your x axis. Okay, and this is your y axis. Okay, so what I have told, that we have considered that electric field is in x direction. Okay, so your electric field is in x direction. So let us suppose along x we have taken this EX. Okay, this magnetic field along y direction. So what is the meaning of this? That magnetic field H is along y direction. Okay, and the direction of propagation of wave, both are mutually perpendicular to each other. Okay, this it is y and this is x, so obviously x and y axis are mutually perpendicular, so this is also mutually perpendicular. And now the direction of propagation of the wave is, this is the direction of propagation of the wave, and this is along z direction, so this is your AZ. Okay, and this is the direction of wave propagation. This is what? This is the direction of wave propagation. Okay, so this way we can understand. Okay, so electric field vector is in which direction? AX direction. So this one is your AX direction. That's why we have represented EX. Your magnetic field is in AY direction. So this is your AY direction, let's say. So that's why we have written HY. Okay, and E and H lie in the same plane. See, if you will consider this XY plane, so this E and H lie in the same plane. Yes or no? So that's why we call it plane waves. Plane waves means electric field vector and magnetic field vector lie in the same plane. So here also, see, this is x axis, this is y axis. So this xy plane is same plane, and E is along x and H is along y. So both lie in the same plane. Okay. But E and H are the functions of Z and T only, because E is along x direction, but the direction of propagation of wave is along Z. So E is also having the Z and T. Okay, so this E and this H. Okay, so E and H are the functions of E and H are the functions of Z and T only. Z is what? This direction Z space. Okay, and t is what? Time, because the wave is propagating with respect to time. So with respect to a space, that is along z axis, and with respect to time, so E and H both are the functions of z and t. Okay, and also E vector is mutually perpendicular to the H vector. So this is also important, that E is perpendicular to H. Okay, so here also see E vector and H vector both are perpendicular. Okay, so EM waves are also called transverse electromagnetic waves. Okay, so the EM waves are also called what? The EM waves are also called the transverse electromagnetic waves. Okay, now from here we will derive the another form of the wave equation. Okay, so consider the wave equation for E and H field, which we had derived in the last class. So considering, so let us consider the wave equation for this E and H fields. Okay. Now, what are the expression for E and H we had derived in the last class? So that is del 2E equals to what? Mu sigma del E upon del T plus this mu epsilon del 2E upon del T square. And this is your equation 1. Another is what? Del 2H equals to mu sigma del H upon del T plus this mu epsilon del 2h upon del t square. This is your equation 2. Okay, now we are considering what is the topic of our discussion. Our topic of discussion is uniform plane waves in free space. Okay, so we will put the conditions of free space here. Okay, so for free space, for free space, what are the consideration? Sigma is 0, that I had discussed, that conductivity in air or free space is 0, and your epsilon will be what? Absolute permittivity, because for free space, if it is a medium, it is epsilon, that is equal to epsilon 0 epsilon r. But if it is a free space, okay, if there is no medium, it is only free space, so epsilon will be equal to epsilon naught, that is the absolute permittivity, and also permeability will also be absolute, that is mu 0 only. Okay, so substituting these values, so substituting these values in above equations, that is in equation 1 and equation 2. So if we put these conditions in above equations 1 and 2, so what will be the new equation obtained after the substitution? So let us see. So this del 2e, first of all write the first equation after substituting these three conditions. So this equation 1 will become del 2e equals to, in place of mu what we have to write? Mu 0, in place of sigma 0. So this term will what be? This term will be 0, because sigma is 0, so this term is 0. So only we will have this term. So mu, in place of mu we have to substitute mu 0, and in place of epsilon we have to substitute epsilon 0 and del 2e upon del t square. That's it. Okay, so it is mu 0 epsilon 0 del 2e upon del t square, and this is your new equation. So we will put equation 3. And what about equation 2? Here also sigma is there, so first term will be 0, because sigma is 0 for free space, so first term is 0. So for the second term we will write del 2h equals to mu 0, sorry, okay, mu 0 epsilon 0 del 2h upon del t square. Is not it? So this is your equation 4. Okay, so in this way we have obtained these two equations. Okay, now we will expand this. So what is del 2? If we talk about del 2, you might be remembering the second unit we had discussed this del operator. So del is what? Del del x plus del del y plus del del z. So del 2 will be del 2x, this del 2x upon del x square, del 2e upon del x square, del 2e upon del y square, and del 2e upon del z square. So in this way we can expand this, yes or no? So let us expand this third equation. So what is our third equation? Our third equation is del 2e equals to mu 0 epsilon 0 and del 2e upon del t square. Okay, this was our third equation, yes or no? So we have to expand this del 2e. Okay, so if we expand this del 2e, so what we can write? So we can write this del 2e equals to del 2e del x square plus del 2e del y square and plus del 2e del z square. Okay, and this is equal to your mu 0 epsilon 0 del 2e upon this del 2 square. Okay, and let us put this as equation 5. Okay, but the wave travels in z direction. Okay, so what is the direction of traveling of the wave? I had discussed just now. So but the what is the direction of propagation of the wave? So the wave travels in z direction. So wave travels in the z direction, and hence your E, yeah, that is electric field intensity, is independent of this x and y. Okay, so the wave travels in z direction, that's why the E is independent of x and y. Okay, yes or no? Because if the propagation is in z direction, so there is no component of E in the x and y direction. So why do we take this del x square and del y square? We will not take it. We will take this one only, that is del 2E upon del z square, because the wave travels in z direction only. So whatever change we are having in E with respect to z, that we will consider. So this is not considered. Okay, so this del 2E upon del z square equals to mu 0 epsilon 0 del 2E upon del t square. Okay, yes or no? So this is one way of representing it, and from here if we want to take this del 2E upon del t square, so what will be the value? Del 2E upon del t square is equal to 1 upon mu 0 epsilon 0 del 2E upon this del z square. Yes or no? Okay, so this one is your equation 6. This is your equation 6. Fine. Now if you talk about the speed of light, so we all know that speed of light is 3 into 10 to the power 8 meter per second. Yes or no? So from where this has been derived? This is this one. Okay, so this V equals to 1 upon root under mu 0 epsilon 0, and this one is your C, and this C is your speed of light. This C is equal to 3 into 10 to the power 8 meter per second. If you want to calculate, you can calculate. You have the value of mu 0, you have the value of epsilon 0. Okay, and 1 upon root over, if you will calculate, you will get this value around 2.99 or something. 3 into 10 to the power 8 meter per second. This is what? This is the velocity of light. So that's why we say that light waves are the EM waves. Okay, because the speed of electromagnetic waves is considered the speed of the light. Okay, so from here we have got this 3 into 10 to the power 8 value. Okay, so here it is 1 upon root under mu 0 epsilon 0. So if we have to write 1 upon mu 0 epsilon 0, so certainly this is what? This one is the V square. Okay, so that we can write or not? So substituting this in equation 6, and we have the value del 2E upon this del t square is equal to this V square and del 2E upon this del z square. Okay, and why we have written V square? Because it is 1 upon mu 0 epsilon 0 and V equals to 1 upon root over of mu 0 epsilon 0. So if we want to represent or replace it with this value, then we have to write V square. Okay, and this is another form of the wave equation. Okay, this is another form of the wave equation, and this is for the free space. Okay, So similarly, if we write for H, so similarly we can write for H directly. We can write, no need to derive because the expressions are same. So for H also we can write this del 2H upon del T square equals to V square into del 2H upon del Z square. Yes or no? So this is for what? This is for the magnetic field intensity. So everywhere whenever you will talk of the EM waves, you will have the two components, one for electric field, another for magnetic field. And this is the another form of both of these equations. This represent this another form, of wave equation. Other form of the wave equation. Okay, is not it? So this way we have derived, our equation. Now if we talk about the phase velocity, so the phase velocity of uniform wave is defined as the velocity with which the phase of the wave propagates. So it is the velocity, the phase velocity is defined as the velocity with which the phase of the wave propagates. Okay, so it is denoted by Vp, okay, or V. So phase velocity is given by, so it is given by V equals to Vp and equals to this dz upon dt. Okay, the rate of change of z with respect to t, and this is equal to the omega upon beta. Some new terms will come across, but we will discuss the new terms further. Okay, so v equals to this phase velocity equals to omega upon beta, where this beta is equals to omega root over of this mu 0 epsilon 0. Okay, and this is called the phase shift constant. Is called the phase shift constant. It's called the phase shift constant measured in radian per meter. Okay, so these terms will come further also, and whenever it is required to define, I will define later.